pleasure to be here today. I have a lot to talk about, so I'm going to start immediately just with a recognition of the work that is being put in front of you today is being carried out by a large number of graduate students who work with me in the laboratory, and without them this presentation would not be possible. So I'd like to thank them. I have a number of things to get through. I'm going to start off with an introduction to breast microwave imaging. I'll talk a little bit about our research progress in this area, and then I'll talk also about scatter imaging, which is another area of particular concern to us, particularly in CT, largely cone beam CT and breast CT, and then I'll move on to discussions of our research progress with positron emission tomography. And then towards the end, I'll wrap up by introducing some machine learning areas that we're starting to introduce into our research, which is possibly of great interest to people in the audience. Right, so why are we here? Why am I interested in imaging, and particularly why am I interested in breast imaging? One of the challenges that we face is that breast cancer is one of the most commonly diagnosed cancers in the world. 140 out of 184 countries, it's the leading cancer present, and in my own province of Manitoba in Canada, it's 25% of the cancer incidence is accounted for by breast cancer. What is well known is that this tends to be a disease of the developed countries where we see high incidence rates in places like North America and Europe. What is less well known is that the mortality rate, while low in those countries, is higher in other parts of the world. And the developing countries see about 50% of all breast cases, and unfortunately 58% of the deaths are associated with breast cancer incidence in the developing countries. And so the challenge that we face is that mammography screening, which is the typical approach that we take today, is only really feasible in regions where there's good health infrastructure. And to try to overcome this is a challenge in some of the low and middle income countries where there tends to be a cultural, financial, and infrastructural challenges that we have to overcome. So our aim is to improve breast cancer screening. We're looking at trying to do this by developing low-cost portable devices that use microwaves that will be of provide greater availability to breast cancer screening for women in low and middle income countries. And so this will ultimately place healthcare in the hands of women, and we hope that this will help them be detected more earlier than they're currently able to be detected, and ultimately this will save lives. So currently there are 3 commercial technologies for breast cancer detection. Mammography is the best, the most well-known, but we also use magnetic resonance imaging and ultrasound, but they have their own limitations as well. Mammography, as I said, uses ionizing radiation, which if we use too much of it can in fact cause cancer. And so it's not an ideal source of radiation. It has a relatively large false positive rate, which means that out of 1,000 women that come into a breast screening program, only 1 of them will have cancer, but 100 of them will be detected by having an abnormal mammogram initially. And this is a challenge because it puts greater pressure on the infrastructure. It requires breast compression, which is uncomfortable for many women. It needs a good, as I said earlier, human and capital infrastructure. And it's also not ideal for dense breasts, and so we can't really use X-ray mammography for younger women. So microwave imaging is a modality that overcomes some of the challenges we see with the general global health requirements. We have issues such as sensitivity, availability, low cost, comfort, and specificity as features that we want to look at, and things such as mammography meet some of these, but not all of them. The same is true of MRI, and the same is true of ultrasound. Whereas microwaves are non-ionizing, so they're safer, we can use them more regularly. It's more sensitive to the tissue contrast, and this is largely driven by the fact that the blood flow in near a malignant lesion is greater than in the surrounding tissues, and this leads to higher conductivity, which is one of the contrast mechanisms that we see with microwaves. It's low power, less power in our systems than what you find in a cell phone, and it's relatively inexpensive compared to X-ray or MRI. It's also quick and comfortable. And so ultimately, if we map microwave imaging onto this, hopefully it improves availability, particularly in these low and middle income countries. It's lower cost than many of the other systems. It doesn't require breast compression, and it's relatively specific and sensitive. So what is breast microwave imaging? Well, simply put, we start off with an antenna which is a transmitter of our microwaves. We irradiate the breast. We're looking for scattering coming back from the tissues lying within the breast. And because of the high contrast associated with the tumor, we're looking for a greater reflection coming back from this region over the soft adipose tissues or the fibroglandular tissues within the breast. Some of the challenges we face is we have to maximize the coupling of the microwave power into the breast tissue. The skin is the greater reflector of the microwaves, and so we have to overcome that. We are looking at various different electrical properties of our tissues, and here you can see the high permittivity and conductivity associated with the tumor is what gives us the group contrast that we're hoping for. We also have to look at our losses within the tissue, particularly at the higher frequencies where there's greater losses. But once we get inside the skin, there's also challenges associated with those attenuations that's taking place and the power drop-off as a function of distance. To overcome resolution issues, because obviously microwaves, although they are of low power, they are of low frequency as well, and the low frequency means longer wavelengths, which means less inherent resolution. And so to overcome this, in radar-based imaging at least, we can do this by increasing the bandwidth, and we're looking at frequencies from 1 to 8 gigahertz, and we can irradiate the breast from a number of different angles, and increasing the number of angles also increases our resolution of detection. As far as the antennas are concerned, we're looking at high-gain antennas that are small in size. We typically want to pack a large number of antennas into our system. We have to minimize antenna coupling between the individual antennas. And so we're looking at wide bandwidths, small antenna size, high gain, and directivity as well. And this is a challenge with respect to antenna design. And so at the end of the day, this is an ongoing research effort to try to find small wideband antennas. And finally, we have to optimize the reconstruction algorithm to improve the resolution. Because unless we can detect those small lesions, we're not going to be able to have early detection. We need to improve our contrast and sensitivity, and we need to improve our specificity, or the reduction in false positives. We've looked at a number of different antennas, and I'm not going to talk much about this today, except to say that we've looked at a variety of antennas, from valves through patch, various horn antennas, spiral conical antennas, even spintronic sensors, which are solid-state devices which allow us to detect microwaves directly. Our system is a Health Canada approved device for medical device testing. The woman lies prone, the breast is pendant through into the examination region. Our antennas rotate around the breast through 360 degrees. They can be raised and lowered over the length of the breast as well. And we can replace the antennas for testing purposes with a number of different structures. And finally, these are processed to give us the reconstructed image. Obviously, for testing purposes, we need realistic phantoms, that we know where the tumor is and we know what the characteristics of that breast are. And so what we do is we take MRI data of the breast, we process this to allow us to obtain a CAD model. We do that by blurring, by filtering the tissue here to get rid of some of the smaller structures. We extract the fibroglandular region and the outside shell of the breast, and these can both be filled with tissue-mimicking liquids, which mimic, in the one case, fibroglandular materials, and in the other case, the soft fatty tissues. The tumors are also 3D printed and filled with, again, a liquid which mimics the tumor. And this allows for realistic tumor analogs, which we place inside the breast in a variety of different positions. We have an array of breast phantoms of different sizes and breast densities, which can be combined to give us a whole suite of variations which are used for testing purposes. And finally, these systems are used within our device for testing. So how have we gone about reconstructing our images? Well, historically, we used what was called a holographic technique, or also the other techniques not used in our lab, but called the delay, multiply, and sum, or delay and sum techniques. These have proved to be less than ideal, and so we've moved to using an iterative approach, which is based on the maximum likelihood expectation maximization approach that's typically found in positron emission tomography, which I'll talk more about later. And so the process is we start off with an initial object estimate. We do a forward projection of that, of the current estimate into the time domain into which we're doing the reconstructions. We then look at the ratio of the measured data to what we've estimated, And then we use that ratio to back project into our original data set. And so we update this, and we can iterate this over a number of different iterations, so moving hopefully closer and closer to the measured data. We use a simple radar model in the forward projection. The back projection uses a variety of different approaches, in this particular case a delay and sum method. And the advantage of using an iterative approach is that we can actually build the physics of the system into both the forward and the back projected data. Our first challenge is that we measure our patient's information in the frequency domain. And so we need to find some way of converting this into the time domain, and this is what's typically called a sinogram. It's not very clear in this particular case, but it ultimately has a sinusoidal form of the data as we rotate around the breast. And so the first challenge is to do this, and early on, typically we would use a fast Fourier transform to do this. But we found again that the resolution there was not as good as we would have liked. And so we've moved to using an inverse Z chirp transform to carry out this process. And so that allows us to actually sample much more finely in the time domain than we can with the inverse Fourier transform, and has certainly improved our results as are shown in this set of slides. This would be typically the results. You can see the temporal component, which is associated with penetration to the breast, is somewhat crude, whereas with the inverse Z chirp transform, we get a much smoother and higher resolution image. We also then looked at a variety of different reconstruction approaches, and we've looked at iterative delay and sum approaches, and iterative delay multiplying sum approaches, as I said, to update this reconstructed image. And as I said, we can implement various factors into this to try to help improve the quality of our image. To date, what we've done is we've implemented the antenna characteristics, so such things as the beam pattern of this antenna, because we're working in the near field, so we have a very complex and complicated antenna beam pattern, and also the output pulse corrections, which in the ideal signal model is just a delta function, but in practice isn't. And so using the iterative delay and sum approach compared to the standard delay and sum gives us, again, much better contrast and reduced noise in the image compared to the non-iterative approach shown here. We measure typically things such as the signal to maximum ratio and the signal to contrast ratio. Those are metrics that we use to actually evaluate the quality of our images. And again, you can see significant improvements in these characteristics for this particular image. As far as the pulse modeling is concerned, we use a Gaussian pulse with a full width half maximum of 0.3 nanoseconds, which is very close to the extracted experimental value shown there. I'm not sure if anybody can see the small differences down here. And this again gives us small but noticeable improvements, again going from this image where there's no correction to a time pulse corrected image shown here, where we again see small increases in the signal to maximum ratio and signal to contrast ratios. One of the biggest challenges, as I said earlier, is the skin reflections tend to dominate our measured responses. This is the case where we have no skin suppression, and so it's very difficult to see the presence of the tumor responses, which are actually hidden in this high reflectivity. And so this is an ideal case where we've managed to actually remove the effects of the skin. And here you can start to see the effect of the sinogram coming in here, which is actually what is the tumor response that we're looking for. And so to do this, we're using singular value decomposition based skin suppression. It helps us reduce the clutter. And again, you can see, going from this image here to this one here, we have a much cleaner image where the tumor is much more clearly present. We do still have some challenges. You'll see this approach tends to still move the tumor slightly from its original position, and so there's things that we still have to work on in this area. So what about scatter? Scatter is a completely different area of research, and this involves X-rays and gamma rays. And typically, the traditional assumption in X-ray imaging or gamma ray imaging is that the scattered photons are noise and need to be removed. The challenge that we face in this is that the scattered photons actually contribute dose to the patient. And so the patient is not seeing any benefits from this radiation at all. And so our goal is to harness the scattered radiation to help us improve image quality, lower dose, and improve our diagnostic and therapeutic benefits to the patient. There's two major areas, as I said earlier, that this is involved with. One is with cone beam CT, where we're using a large field of X-rays, where there can be lots of scatter. This is particularly true in breast imaging. Again, you'll see the two links in terms of the breast imaging aspects of interest to me. So we see increased dose, poorer image quality, and at the end of the day, with CT in general, we have a challenge because there's an uncertain tissue characterization, because CT measures the linear attenuation coefficient of those X-rays, which is in turn a function of two parameters, both the atomic number and the electron density of the tissue. And so it's a challenge to try to tease this out. As far as positron emission tomography is concerned, again, this is where you inject a radioisotope into the patient and you measure the uptake of that radioactive activity. There's a presence of scattered radiation in that technique in all cases. And so how do we eliminate or make use of those scattered photons? And so there's another area as well that's a challenge, in that any PET imaging requires some metric to calculate the attenuation of those photons in the body. And so one also needs to have some sense of what the attenuation correction is. This requires a sequential CT, or magnetic resonance imaging system, which again drives up the cost of these approaches. We can use diagnostic CT, but it has a different U value because it's working at different energies. And converting the magnetic resonance imaging system results to linear attenuation coefficients are not without their challenges. And so here's a quick example of some of the challenges we face. Here is a linear attenuation coefficient image of a phantom. This shows these regions as basically looking exactly the same, whereas in fact they're made up of two different materials with different electron densities and atomic numbers. And so this system is different tissues, but using scatter imaging you're able to extract both of these parameters. We can show that this can be done using a very simple pencil beam approach, much like was done with CT in its very early days. The challenge that we face with this, whether we do it by simulation or whether we do it experimentally, is that it takes a long time. And so we've actually gone away from this technique, although it does quite well in detecting various different materials within the breast, as is shown in this slide here, where we see very small differences or small errors between the measured values and the actual parameters in terms of electron density of the breast, which is less than 1% for most materials, except for the microcalcifications. And for a more complex and homogeneous breast, again, we get a good agreement between the breast structure and what we reconstruct. As I said, the challenge we face is that this takes a long time. And so we've moved to a cone beam spectroscopic type approach, where we actually use the energy of the detected photons to try to overcome some of the challenges that we face with a pencil beam approach. And this is done by going to a more complex CT reconstruction approach, where instead of using straight lines, which typically is what we've done in most traditional CT mechanisms, where we look at the source and the detector and we reconstruct along a single line, we're looking at arcs. And the reason behind this is that we have a source of radiation here, and it happens to scatter here into a point here. Any scattering along this arc will have the same scattering angle, and therefore will have the same energy. And so by detecting the energy, we actually know along which arc the scattering occurred, and we're able to reconstruct the image using a somewhat more sophisticated, but nevertheless approachable way analytically. The difficulty that we have with this approach is that it's very sensitive to the energy that we detect. And small energy changes can lead to big changes in where that arc occurs. And at the end of the day, that's the downfall of this approach, in that the detectors that we use currently don't have sufficient energy resolution. The one exciting thing about this approach, however, is that unlike conventional CT, which requires a number of projections, which increases the dose to the patient, this approach needs relatively few. This is just an image showing the changing energy resolution of the detector. And so when we have 1,000 electron volts, 1 keV energy resolution, you can see a somewhat crude reconstruction, which improves as the energy resolution gets smaller and smaller. And here's what we have with conventional CT. is if we have 4 projections, you effectively cannot reconstruct anything. As we increase the number of projections, we move slowly towards a much better reconstruction model. Whereas with scatter CT, even with 1 projection, you can see we're starting to approach the result. And as we increase the number of projections up to 8, we're starting to get a much better image reconstruction. So what's our research progress with respect to PET scatter imaging? And here I say it's beyond electron density, because with scatter imaging, we're able to extract not only the uptake of the radioactivity, which is what we get with the standard PET system, we're also able to determine the anatomical information within the body, which allows us to get that attenuation coefficient that we require to do the necessary corrections. Again, we use somewhat of a similar approach to what I showed you with CT, where we're looking at arcs. We have the patient here, there's a source of radiation, and here's the annihilation point. And instead of this photon going on in a straight line to give us what would be normally our trues, this is scattered at this point and ends up here. And so if we were to not correct for this, what we would think is we would think that the annihilation occurred somewhere along this line, which was a false. So we are going to use our arcs in this fashion, and we have a relationship here, which I'm not going to go into, except to say that it takes into account the various photon fluxes, the electron densities throughout the material, the cross-section of scattering given by the Kayamashina cross-section, the attenuation within the body, various detection efficiencies in geometric cross-sections, which we need to take into account when calculating the number of photons reaching the detector. And so here we have the source of annihilation again. The initial photons are traveling off in this direction. This one scatters, is detected here, and so we have these 2 arcs forming, and the electron density is given by an integration over this arc, whereas the annihilation, we know, falls somewhere in between these 2 arcs. And so taking that into account, we can calculate both the activity and the electron density map by solving this generalized scatter maximum likelihood expectation maximization equation. Results. This is what we would see with true coincidences, where we had a perfect system, where there was no scattering involved. If I try to use a conventional approach to reconstruct based on the scattered photons, this is what I would see. It's just complete noise. Whereas if we use our approach, you can start to see an image which looks something like this. Now you may say, well, hang on, this is not as good as this. But just remember, this is done only from the scattered photons, whereas in fact, at the end of the day, we're combining this, the trues, and this together, which helps us improve our image quality while keeping the radiation dose low. And this is effectively the results that are plotted as a function of the contrast recovery. And what we would ideally like to see, of course, is something that's up in this top left-hand corner, where we have the lowest noise and the highest contrast. So anything that's up this way is better. This is the ideal, the solid line here. If I start to add noise to a conventional system, it pushes it down to this corner, which is in the wrong direction. And if I start to use our techniques, it tends to push it up into this corner, which is what we're looking for. And so at the end of the day, we reconstruct both the activity and the electron density in a parallel fashion, updating both of them at the same time, and moving on from something that looks like this initially, in sort of iteration number 1, where you can see, this is our reference, we have a region of hot activity here, this is our electron density distribution here, and you can see that initially we reflect in our initial iterations the lungs. These are simulated, obviously, phantom-like lungs. And slowly, as we iterate, this improves, and the quality of our electron density image improves, as does the quality of our activity image. And this is another one using a standard NEMA phantom, which is used largely for testing these systems. Again, this is only using scattered photons. And again, that's the rationale, the reason why behind the blurring, but at least the regions of hot and cold activity are shown up reasonably clearly. This is where we start to combine both trues and scattered photons at a certain fraction. And again, we get relatively good results in terms of our reconstruction of our contrast of these particular objects. And finally, when we put this all together, this is our ideal phantom, and we're able to reconstruct when we're looking at systems which take into account multiple scattering events, something that looks like this. So we have a number of challenges with these approaches. The microwave imaging approaches, we need to find ways of detecting the tumor out of the structures that we're detecting, or the image that we're getting. Within the scatter imaging world, we need to find ways to account for the fact that the detectors that we're using aren't ideal and don't have the necessary energy resolution that we require. And so what we want to do ultimately is to take this data, feed it into some form of machine learning algorithm, and allow us to do a diagnosis of tumor or no tumor. And this is particularly valid not so much for the bed system that I showed you, but for our portable system, whereby we would like to actually have a result that doesn't require the intervention of a well-trained radiologist to be able to diagnose the presence or absence of a lesion. We see this as a pre-screening device, so it's not meant to replace mammography or magnetic resonance imaging, or PET for that matter. It's meant to be something that we can get out into the field to allow, as a woman to carry out this test themselves, ideally, or have it done at a local clinic. And so we're taking our data, and one of the hopes is that this will allow operator-free diagnosis, and pixel locality in the sinograms that we have has yet to be exploited. And so, our algorithmic approaches don't do this in a big picture sense, and we're hoping that the use of convolutional neural networks will allow us to take this data and detect the presence of a lesion in that, or not, as the case may be. So we've developed even further fibroglandular and adipose shells to allow us to do a larger combination of different breast sizes and breast densities for training our systems. And so initially we had 19 shells. Now we've got up to 66 unique phantoms, which allows us to process a much larger number of systems. And so, 13 unique phantoms initially, which had 249 scans. Now we're up to 66 unique phantoms, and we have 1,008 scans of our breasts. And so we process this data, we do some pre-processing on it, we augment this data to allow us to train a machine learning algorithm to do this. And we do this typically by splitting this into 20% data used for testing, 80% for training. Augmentation allows us to push up the number of samples, and so we have a much larger number of samples to train our systems with than breast phantoms. Again, we use a very traditional approach. We have a variety of convolutional layers, followed by max pooling, convolutional layers again, followed by a final dense layer. And this allows us to look at the ability to detect the presence of a lesion. And in comparison of our system to date, with those results obtained using digital mammography, we do actually somewhat better than digital mammography is concerned, both in terms of the region, the ROC curves, the area under that curve, as well as the diagnostic accuracies, the sensitivity, and the specificities. We've also tested this set to see that it's generalizable by training only on a certain number of shells and then testing on a third shell, which the system hasn't seen. And again, this tends to show good results, and is shown here in comparison with logistic regression, where again, good results are obtained for the CNN approaches that we look at. With respect to PET systems, again, we're looking to try to decrease our computational time, because the iterative approach is time-consuming and computationally expensive. We're looking at trying to improve our image quality and maximize the useful information obtained from those scattered photons. Just showing some very simple analytical simulations, some toy models, as well as some more realistic body phantoms. We take this object, we generate the sinogram for that, which is obtained using the radon transform. We typically add some noise to that system. And then again, we have a system of convolutional layers, max pooling layers, and dense layers, very similar to what we had seen in the previous one. And we look at how well we're able to reconstruct these images given the measured data, which is the sinogram. And again, quite good results are obtained for these toy results compared to the standard filter back projection approach, which is the standard in the industry for positron emission tomography reconstruction with relatively small errors. And again, we're now taking the PET sinogram in all its glory. We're running it through what's called a deep PET convolutional network to be able to reconstruct the image that looks something of this nature. And again, in comparison to what we get with standard filtered back projection approaches, we get quite good results in this manner. So again, what we're looking with is mean squared error or structural similarity. Here, lower is better. So again, the filtered back projection does slightly worse than the CNN approach does. For structural similarity, we again do slightly better than the filtered back projection approach. And we're taking this now one step further with, rather than just using the whole sinogram for the photopeak region, which is the typical approach, which represents the trues, those that aren't scattered, we're actually reconstructing the image using different regions of the energy spectrum. This is a function of energy. This is the number of counts. And the scattered photons are those that typically lie down on this side of the photopeak, which is this region here. And so by looking at each of these regions independently, they each have their own sinograms. We're able to train our system based on that. And in this way, we're able to overcome some of the challenges that we face with the analytical approaches, which require very high energy resolution detector systems, which are not yet available. So in conclusion, our machine learning really has demonstrated improved results, both in terms of the area under the curve of the ROC curve and diagnostic accuracy. This is for the microwave sensing. We're looking to evaluate the benefits of this with a much larger data set. We're going to then try and evaluate and implement methods for tumor size and location prediction, so going beyond just the point of just detecting the presence or absence of a lesion. We're looking at comparing the classifier performance to image reconstruction techniques. Again, how well does the classifier do in comparison to an expert reader of the image? And we're going to evaluate the role of tumor size and location on the ability to detect that tumor. As far as PET scatter machine learning is concerned, we have to date demonstrated that they're capable of improving the reconstruction of activity and electron density distributions. We know that the algebraic reconstructions are sensitive to detector energy resolution, and that the CNN reconstructions have lower MSE and higher structural similarity. The challenge is, can we use this approach to train the machine learning system to look at the whole energy spectrum and to reconstruct valuable information of the scattered photons from that. With that, thank you very much indeed for your attention. I'd like to thank a number of bodies who provide funding for this research, and I think I still have some time for questions. Thank you.